A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
You see it in the movies all the time. A missile is launched, an interceptor meets it in the sky, and there is this massive cinematic orange fireball that just consumes everything. It looks like the threat is just deleted from the sky. But when you look at actual footage from recent events, especially some of the high-altitude footage we have seen over the last year, it looks nothing like that. It is more like a silent, white flash followed by a shower of glowing sparks that seem to float for an eternity. Today's prompt from Daniel is about the physics behind that reality, specifically the fluid dynamics and kinetic mechanics of atmospheric missile interception. He wants to know why things break the way they do, and why the debris dispersal is so much more complicated than just a simple explosion.
It is a great prompt because it hits on the fundamental difference between what we call a blast fragmentation kill and a hit-to-kill interception. I am Herman Poppleberry, by the way, and I have been looking forward to this because the physics of the atmosphere changes every single variable compared to what happens in the vacuum of space. When we talked about space interceptions in episode 1194, we were dealing with pure Newtonian mechanics. In the vacuum, there is no air resistance to slow down the debris or change its trajectory. But once you bring that collision down into the atmosphere, you are adding fluid dynamics, thermal heating, and aerodynamic drag into a mix that is already happening at hypersonic speeds.
And that is the part that always catches people off guard. We are talking about speeds that are difficult to even wrap your head around. If an interceptor is moving at Mach 7 and the target is coming in at Mach 5, that closing speed is 12 times the speed of sound. At those velocities, the materials do not even behave like solids anymore. They behave more like fluids upon impact. This is the kinetic kill window, Herman. Why is the atmosphere specifically the hardest place to make this happen?
It is the hardest because the atmosphere is essentially a thick soup that gets denser the lower you go. When you are in space, you have all the time in the world to calculate a trajectory. But in the atmosphere, you are dealing with aerothermal heating. The air itself is trying to melt your interceptor before it even reaches the target, and then there is the pressure. At Mach 7, the air in front of the missile is compressed so much that it turns into a plasma. This creates a communication blackout and makes sensor data incredibly noisy. You are trying to hit a needle with another needle, while both needles are wrapped in a layer of white-hot gas.
So, when we talk about hit-to-kill, we are moving away from the old-school method. In episode 936, we talked about proximity fuses where you just had to get close and blow up a grenade in the sky. Why did we move away from that?
Because at hypersonic speeds, a fragmentation cloud is often too slow or too light to actually stop the momentum of a heavy warhead. If you just pepper a re-entry vehicle with small holes, it might still hit its target. Hit-to-kill is about total energy transfer. You want to put all the mass of the interceptor directly into the mass of the target. It is the difference between throwing a handful of sand at a moving car and throwing a brick. The brick stops the car. The sand just ruins the paint.
Let's get into the actual mechanics of that impact. When these two objects meet at several kilometers per second, you said they behave like fluids. Walk me through the first microsecond of that collision.
It is fascinating. At these hypervelocities, the impact pressure far exceeds the yield strength of any known material. Steel, titanium, carbon fiber, it does not matter. Upon impact, a shock wave travels through both vehicles at the speed of sound within that material. Because the collision speed is higher than the speed of sound in the air, but comparable to the speed of sound in the metal, the materials undergo what we call fluidization. They flow. The kinetic energy is so high that the chemical bonds holding the atoms together are momentarily irrelevant. The energy is dumped into the internal structure so fast that the target does not just break, It undergoes a phase change in some areas and a total structural disintegration in others.
This is where the material science comes in. Daniel asked about the structural integrity of these rockets. If I have a missile made of high-grade titanium versus one made of modern carbon fiber composites, how does that change the way they die in the sky?
It changes the debris field entirely. Titanium is incredibly tough and ductile. When a kinetic interceptor hits a titanium airframe, the metal tends to tear and shred into large, jagged plates. These plates have a high ballistic coefficient, meaning they cut through the air effectively. They stay dangerous for a long time. Carbon fiber, however, is brittle. It is incredibly strong until it reaches its limit, and then it fails catastrophically. It shatters into millions of tiny needles and dust.
So, from a defense perspective, you actually want your enemy to use carbon fiber?
In a way, yes. Those tiny fragments have a very low ballistic coefficient. The atmosphere acts like a giant filter. As soon as the carbon fiber shatters, the air resistance hits those tiny pieces and slows them down almost instantly. They lose their kinetic energy and drift down like ash. But a large chunk of a titanium engine block? That is going to keep moving at Mach 4 or 5 even after the rest of the missile is gone. It becomes a secondary projectile.
You mentioned the hydrodynamic ram effect earlier when we were prepping. Does that apply to the fuel tanks? Because most of these missiles are basically giant flying gas cans.
Think of a liquid-fueled ballistic missile like a giant thin-skinned soda can. Most of its volume is just empty space filled with liquid oxygen or kerosene. When a kinetic interceptor hits that, it is not just hitting metal, it is hitting a non-compressible liquid. The impact creates a massive pressure wave through the fuel. This is the hydrodynamic ram. The energy of the impact is transmitted through the liquid to the walls of the tank at the speed of sound in that liquid. The tank does not just get a hole in it, it unzips. The entire structure shreds from the inside out because the liquid has nowhere to go. This is why you see those large, shimmering clouds in interception videos. That is the fuel being atomized into a fine mist.
And if it is a solid fuel rocket?
Then it is like hitting a giant rubbery log. Solid propellant is dense and has its own structural integrity. It does not atomize. Instead, it breaks into large burning chunks. This is actually much messier for the defense system because you now have several tons of burning propellant falling toward the Earth. It is not a mist that dissipates, it is a rain of fire.
This brings us to the debris cloud evolution. Once the hit happens, the atmosphere starts sorting the pieces. You use the term ballistic coefficient, or beta. Can we break that down for the listeners? Why does the air care about the shape of the trash?
The ballistic coefficient is essentially a ratio of an object's mass to its surface area and drag coefficient. Imagine you are standing on a bridge and you drop a bowling ball and a feather at the same time. In a vacuum, they hit the water together. But in the atmosphere, the bowling ball has a high beta. It is heavy and has a small surface area, so it ignores the air. The feather has a low beta. It is light and has a huge surface area relative to its weight, so the air wins. After an interception, the atmosphere performs a massive high-speed sorting operation. The heavy, dense parts, the warhead casing, the engine turbopumps, the guidance computer have high beta. They maintain their forward momentum and follow a predictable ballistic arc. The light parts, the skin of the rocket, the insulation, the wiring, have low beta. They hit the atmospheric wall and are pushed off course, slowing down rapidly and drifting for miles.
So when the defense systems are calculating where the debris will fall, they're not just looking at one spot, they're looking at a footprint.
A debris footprint or a ground hazard area. This is where the math gets incredibly stressful. The alerting systems have to calculate the most likely impact zone for the dangerous bits. What is fascinating is how the altitude of the interception changes this footprint. If you intercept at 40 kilometers up, in the stratosphere the air is thin. The debris can travel a long way before it really starts to feel the drag. This creates a massive, wide footprint that might span several counties. If you intercept at 10 kilometers, the atmosphere is much denser. The debris is slowed down much faster, which narrows the footprint but increases the concentration of the impact. You are trading a wide area of light debris for a small area of heavy, high-velocity debris.
I want to talk about the report from DARPA that came out in January of 26, the Aegis Atmospheric Study. They found that debris dispersal in the stratosphere was actually 40% more chaotic than our previous models suggested. They attributed this to something called the Mach stem effect. Herman, can you explain how a shockwave can make debris more chaotic?
This is one of the most complex parts of fluid dynamics. A Mach stem occurs when shock waves interact with each other. When the interceptor hits the target, it creates a primary shock wave. But because this is happening at hypersonic speeds, that shock wave is moving through a medium that is already being compressed by the target's own bow shock. The wave of air the missile is pushing in front of itself. When these waves intersect, they don't just add together, they create a third, even more intense shock wave called a Mach stem. This wave can actually be stronger than the sum of the two parts. It can cause structural failure in parts of the missile that were not even near the point of impact. It is like the air itself becomes a hammer that shatters the rocket from the outside in. This is why we see these bizarre fragmentation patterns where the tail of a rocket might just snap off even though the hit was at the nose. The Mach stem travels down the body of the missile and finds a weak point, like a joint or a bolt, and shears it instantly.
That explains why the DARPA study was so worried. If the air itself is acting as a secondary interceptor, it makes the debris field asymmetric. You might expect the debris to go straight, but the Mach stem kicks a 300-pound engine block 40 degrees to the left.
And that is a nightmare for radar systems. This leads into the second-order effects we need to discuss. When a missile breaks up, it creates thousands of pieces of debris. To a radar system, each one of those pieces can look like a potential warhead. This is the false target problem. If you have one warhead and 9,000 pieces of shimmering aluminum foil and jagged titanium, how does the defense system know if it actually killed the threat?
It is like a magician throwing a handful of glitter in the air to hide a coin.
Precisely. Modern systems use discrimination algorithms to look at the way each piece of debris moves. Remember the ballistic coefficient? The radar tracks how fast each object is slowing down. If an object is slowing down quickly, the computer ignores it. That is just a piece of the skin. But if an object is maintaining its velocity and following a perfect ballistic curve, that is likely the warhead. The problem is that in the first few seconds after impact, everything is moving so fast and is so hot that the radar can be blinded by the sheer volume of data. This is why terminal guidance is so important. You have to hit the target so hard and so precisely that you don't just break it, you destroy its aerodynamic stability.
Let's look at a case study. In late 25, there were those high-altitude interception tests over the Pacific. The data showed that even when the kill was successful, the debris dispersal was highly nonlinear. Herman, what did we learn from those specific tests regarding the ground footprint?
Those tests were a wake-up call. They showed that at Mach 8, the thermal energy released during the collision is enough to partially melt the debris. We saw liquid metal rain for the first time in a controlled test environment. The debris wasn't just solid chunks. It was molten droplets of aluminum and titanium that re-solidified as they fell through the cooler layers of the atmosphere. This changed their shape and, therefore, their ballistic coefficient mid-flight. It made the ground footprint almost impossible to predict with traditional Newtonian models. The January 26 DARPA report basically said we need to move to machine learning models that can predict these shape-shifting debris patterns in real time.
It makes me think about the people on the ground. When the sirens go off, they are told to stay in a protected space for 10 minutes after the interception. That 10-minute window is exactly what we are talking about. It is the time it takes for the debris with a lower ballistic coefficient to finally reach the ground. People think if they hear the boom, it is over. But that boom is just the beginning of the debris fall.
That is the most important practical takeaway. The acoustic signature of the interception travels at the speed of sound, which is roughly 340 meters per second. But the debris is governed by gravity and drag. Depending on the altitude, it can take several minutes for the shrapnel to rain down. And because it is often falling at terminal velocity, which for a heavy piece of metal can be hundreds of miles per hour, you might not even hear it coming until it hits. It is a very different kind of threat than the missile itself, but it is one that the physics of the atmosphere makes inevitable.
We also have to talk about the plasma shield problem. You mentioned it briefly, but it is a huge factor in why these interceptions are so technically difficult.
Right. When you are moving at hypersonic speeds, the air in the stagnation point at the nose of the interceptor is compressed so violently that its temperature spikes to thousands of degrees. This strips the electrons off the air molecules, creating a layer of plasma. Plasma is electrically conductive, which means it reflects radio waves and absorbs certain infrared frequencies. It is like trying to look through a frosted window that is also on fire. Interceptors like the latest versions of the Patriot or the Arrow 3 have to use specialized windows made of sapphire or other heat-resistant materials, and they often use coolant injection, where they spray a gas over the window to keep the plasma from touching it. If the seeker head can't see the target through its own plasma, it misses, and at Mach 7, a miss of even 10 centimeters is a total failure.
This brings us to the center of mass problem. Daniel's prompt asked about structural integrity. If you hit the tail of a missile, you might knock it off course, but the warhead is still intact. The goal is always a lethal hit on the warhead itself.
Yes, and that requires incredible precision. You are trying to hit a target the size of a trash can while it is moving at 5,000 kilometers per hour, with an interceptor moving even faster. If you hit the engine section, the warhead might continue on a tumble trajectory. It won't hit its intended target, but it will still fall somewhere, and it might still be armed. A low-order detonation can occur where the warhead is crushed, but the explosives don't fully detonate, spreading radioactive or chemical material over a wide area. This is why terminal guidance is the holy grail of missile defense. We don't just want to hit the missile, we want to hit the brain or the heart of the missile.
So, looking at the engineering trade-offs, is it better to intercept high or low?
It is a strategic gamble. If you intercept high, in the stratosphere, you have more time to try again if you miss. But the debris footprint is massive and unpredictable. If you intercept low, in the troposphere, the debris footprint is small and the air resistance helps destroy the fragments, but you have almost zero margin for error. If the interceptor fails at 10 kilometers, the warhead hits the ground in seconds. Most modern defense architectures use a layered approach for this exact reason. You try to get it high with something like an Aegis system or a THAAD, and if that fails, you have your point defense, like the Patriot or the Iris-T waiting at lower altitudes.
We are reaching a point where the speed of the missiles is outstripping our ability to model the debris perfectly. If the DARPA study says we are 40% more chaotic in our predictions than we thought, that is a huge margin of error when you're talking about tons of falling metal. Is there a limit to what kinetic interception can achieve?
I think we are approaching it. When you get into the Mach 10 to Mach 15 range, the true hypersonic glide vehicles, the kinetic energy is so high that the debris is essentially a cloud of plasma and vapor. At those speeds, the atmosphere itself becomes the primary weapon. The challenge isn't just hitting the target, it's surviving the environment long enough to get there. This is why there is such a massive push toward directed energy.
Lasers, high-power microwaves. That is the shift we are seeing in the January 26 report. Why is a laser better for debris management?
A laser doesn't hit the target with mass, it hits it with photons. It uses thermal energy to cause a structural failure. If you can use a laser to melt a small hole in the skin of a pressurized fuel tank, the internal pressure will cause the missile to unzip itself. Because you aren't dumping a huge amount of external kinetic energy into the system, the debris tends to follow the original trajectory more closely. It is more predictable. Also, a laser can dwell on a target, heating it up until the propellant ignites, potentially vaporizing more of the structure before it even starts to fall.
But even then, you still have the debris. You cannot escape the conservation of mass.
You can't make the matter disappear. You can only change its state. Whether it is a solid block of steel or a cloud of vaporized titanium, that mass is coming down. The goal of all this complex fluid dynamics and kinetic modeling is simply to ensure that when it does come down, it is in the least dangerous form possible over the least populated area possible.
It really reframes the whole idea of a missile shield. It is not a solid dome. It is more like a giant blender in the sky. It takes a concentrated threat and turns it into a dispersed one. And the goal is to make sure that dispersal happens in a way that the atmosphere can handle.
That is a great way to put it. It is a kinetic blender. And the blades of that blender are the laws of physics, drag, gravity, and thermodynamics. We are just trying to aim the blender.
I think about the rarefied gas dynamics you mentioned earlier. As you go higher, the air molecules are so far apart that they don't even act like a fluid anymore. They act like individual billiard balls.
Right. That is the transition from continuum mechanics to rarefied flow. When an interception happens at the edge of the atmosphere, the debris doesn't feel any drag at first. It maintains its velocity perfectly. But as it falls, it hits the continuum layer, the denser air, and it is like hitting a brick wall. This is where the most violent structural breakup happens. It is called Mach's Q in reverse. The dynamic pressure spikes so fast that the fragments are crushed by the air. If you can trigger that breakup high enough, the atmosphere does most of the work for you.
It is a violent, beautiful, and terrifying process. Daniel, I hope that gives you a better sense of why those interceptions look the way they do. It is not a Hollywood explosion because there is no fire, in the traditional sense. It is just the raw, brutal conversion of kinetic energy into heat and structural failure.
It is a mix of high-speed fluid dynamics, material science, and the sheer overwhelming power of velocity squared. We have covered the physics of the collision, the sorting by the atmosphere, and the reality of the ground hazard. It is a complex system, but a fascinating one.
Definitely. Well, thanks as always to our producer, Hilbert Flumingtop, for keeping us on track and pulling all the data for this one.
And a big thanks to Modal for providing the GPU credits that power the research and generation of this show. We literally could not do these deep dives into the math of the Mach stem effect without that kind of compute.
This has been My Weird Prompts. If you're finding these deep dives useful, or even just a little bit terrifying in a cool way, a quick review on your favorite podcast app really helps us out. It is the best way to help other people find the show.
You can also find our full archive, including those related episodes on space interception and kinetic kills at myweirdprompts.com. We have over 1,200 episodes there now, so there is plenty to explore if you want to go down the rabbit hole of defense tech.
We are also on Spotify and Apple Podcasts, so make sure you are subscribed there so you do not miss the next prompt from Daniel, or whoever else decides to send us into a physics spiral.
Thanks for listening. We will catch you in the next one.
See ya.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes